I'm a PhD student at Stanford, advised by Professor Fei Li, and today I'll be discussing the topic of generalization through task representations with foundation models. So as a field, it has really been one of the North Star to build kind of the robot that operate in the open world. I think this video from the Stanford Personal Robotics program almost 20 years ago really exemplifies the pursuit, right? Where the robot enters a household environment, just tidies up the space, except all was great, except it was teleoperated. So what is really the desiderata, right? So it is actually really obvious, I think, from a high level, because we would like a robotic system that takes in instruction and raw sensory observations and outputs the next action. So importantly, this system should generalize across any environments and across any tasks. By environments, I mean the variations in scene and robot configurations, as well as new objects. By tasks, I mean the variations in goals, motion, and skills. So in fact, we have made tremendous progress in the past few years as a field. So diffusion policies with its wide adoption can effectively model the kind of the action distributions, multimodal action distributions, as well as the emergence of vision language action models. These are the models that are, the policies that are kind of fine-tuned from the VLMs to leverage this rich semantic knowledge. And the recent release, I think, from the from physical intelligence, the Pi 0.5, is really perhaps one of the kind of the culminations of these efforts, where they show a single model can achieve this truly remarkable generalization in unseen kind of household environments. However, there's a quote from the paper. It's clear that this quote is like, its goal is not to accomplish new skills, but to generalize to new settings. So it's clear that kind of this generalization across tasks still remains kind of the unsolved problems or something that's out of the scope. While we can be optimistic that scaling data will eventually get us there, in my opinion, if we want to tackle this from a more scientific perspective, as well as from a more practical perspective, if you want to care about what data to collect and how to collect them, we need to have a deeper understanding of the fundamental question for this task level generalization, which is what is a task and how to represent it. So this seems like a trivial question for some of the domains, for example, like the Roomba robot and also the self-driving car, where you either have to cover as much area as possible or just going from point A to point B. But for like a robot butlers in our home that we desire, when it comes to manipulation, it's really not a trivial question. For example, if you look back at this video from the beginning, what is really the task and how do we communicate to the robot, right? So first of all, maybe you think maybe it's a very sensible choice, of course, I think, to decompose it to multiple subtasks like place container, organizing pillows, sorting books, packing toys, etc. But there are so much nuances even for this, like each single task, right? So for example, for placing container, where should the container be placed? Is there enough space to place this? And then for organizing pillows, how do we know how we're supposed to arrange them? Because there are 4 pillows here, maybe we decide that we want to put 2 by 2 on each side, but what if it's a different number of pillows? What if it's 5 pillows? What if it's 6? What if there's also a blanket? And for sorting books, right, the robot is kind of stacking them like by aligning their edges like this. But why does it have to do it this way? Maybe because there's not a bookshelf nearby. Because if there's a bookshelf, then we don't even care we want to stack them in the first place. We will just stow them one by one onto the shelf. And for packing toys, like you realize that this is the last stage of the full task, but the container that the robot placed there in the first place was actually only used in this last stage. So all of these subtasks are kind of interdependent. So they're not just like a simple one after one each subtask. They have rich geometric and also all sorts of rich dependencies, because you need to care about how we should kind of place the container such that the robot is kinematically feasible for the robot to kind of approach the container and also grasp all the Lego blocks and put them in the container. So today I will be introducing some of our explorations in the past few years into this question of what is a task and how to represent it. Basically the question of task representation. And for each work, I'll be introducing one specific instantiation of this. But I want to know that like all of this is now like a they're now kind of proposed to be kind of the final answer. They're more like something that can help us as a field to gain collective knowledge and better understanding towards this really difficult questions. So first of all, I'll be talking about the natural language as kind of the representation. So of course, we all know the rise of large language models in the past few years. And this was back in 2021 in summer. And then we were kind of thinking about, this is like a year before ChatGPT was released. And in this work, we were kind of, it was among the first to ask the question, can we represent tasks in the space of natural language by using kind of large language model for planning? So this seems kind of trivial today, but it wasn't really clear back then. So we investigate this, in this environment called virtual home. It's a simulated household environment. So basically the goal is that you're given a set of admissible skills, and we want to control an embodied agent to kind of complete some meaningful tasks. Some people may have been training machine learning models to do this, but what we're interested in is whether a pre-trained LLM can do it completely zero shot. So it turns out there's some promising sign. So if you, here's an example where you give it some prompt of how you kind of how you decompose the task of shape into multiple steps, and you ask it for a new task. It can give you really sensible answers. But it wasn't perfect back then. It was GPT-3. So this is like my favorite one, I think. So here the task is take kids to school, and if you give us the prompt here, it will say, literally just say, step 1, walk to car, open car door, get kids out of the car, put kids in school bus, close the school bus door, sit in car, and drive to work. And then later, so this is like in this simulation environment, later the folks at Google also built upon this work to introduce SACAN, where they introduced the concept of if you have a value function for each skill, then you can combine this knowledge from the large language model and the value function for each skill to do this multi-task, like multi-step kind of task planning. So later in collaboration with them, we together also introduced a series of work that build upon similar ideas to use LLMs to interpret and represent robotic tasks, like intermodal, codeless policies, POM-E, and grounded decoding. While the idea has been widely adopted in the community, a critical limitation is that robotic tasks are spatial instead of textual. So if you want to learn about how to quickly fold a shirt, I can watch a video and probably learn this in 1 minute or maybe less. If I were given these task instructions, right, I will really struggle to learn this for a much longer time. So how can we convey this kind of spatial task to robots? So here's the idea that we introduced in this work called VoxPoser. So idea is that we want to represent tasks by this concept called 3D value maps. So how it works is that given a natural language instruction, open the top drawer, we want to use foundation models to generate code to kind of iteratively construct this 3D value map. And then we use motion planning to get the actions. So here's a concrete example where the task is open the top drawer. And LLM will generate first like a 3D NumPy array of 100 by 100 by 100 voxel space that represent the robot workspace. And then it will say, let me detect the handles in the scene. And there are like 2 handles here, right? So it will call the vision language model to get all both handles in the scene. And then because we only want the top handle, so we sort them, the LLM will generate code to sort them by their height. And then it will assign a positive value to that location. And then this is like smooth to propagate to the entire robot workspace. And you can also say, also watch out for that vase. And then it will do similar things, but this time it's detecting the vase and assigning a negative value to the location. And finally, also by building upon the previous generated kind of map to have this holistic 3D value map. And then you use motion planning to generate the robot actions for this task. And here's the robot that's grasping the top drawer and then opening it. And also we show this across other tasks too. So all of this is without task-specific data, and there's no demonstration also for that task. And also it's sixed off with both translation and kind of rotation for the gripper. And also it's done at a closed loop frequency at 10 Hertz. So this is like grounding tasks in 3D space. But what about the time dimension? Because there are obviously some tasks that have reach dependencies across different time steps. For example, if for this like pouring tea, you first grasp the handle, and then you want to keep it upright, and then you want to align to the cup, and then start pouring. So if a previous step fails, you shouldn't proceed to the next one. You should probably backtrack to a previous stage. So how do we represent tasks in this way that spans not only the 3D space, but also time? So we want spatial composition and time composition. And what is something that can get us there? So in this work, this follow-up work to the previous one called Recap, we explore this question. So essentially, the high-level idea is to represent tasks by a sequence of key point relations. So basically, and we call this relational key point constraints. So the high-level idea is that each constraint is a Python function that maps a series of, actually a set of key points into a numerical cost. And then a task is represented by a series of this kind of what we call recap functions. And then all of these are used by a constraint optimization solver to obtain the robot actions. Let's walk through a concrete example. Here, the large vision models will give us first the key points in the scene, and then we overlay the key point onto and the scene onto the image, as well as the instruction. We give it to the GPT-4o, and it will similarly generate Python functions this time. But first, it will decompose the task into multiple stages. And then for each stage, it will generate two types of this kind of recap constraints. One is the sub-goal constraints that will say, okay, what the robot should achieve at the end of this stage. And then the path constraints are the kind of constraints that it wants the robot to achieve to maintain within this stage. So for example, one sub-goal constraint for the first stage is grasping the teapot handle, right? So it will say the robot key point is 0.0, and then the teapot handle is 0.1. So we say we want to normalize, we want to reduce the L2 norm between these two key points. And then a similar idea goes for other sub-goal constraints and path constraints. And then concretely for this task, the first one is, of course, like you want to have the robot approach the handle of the teapot. And then in the second stage, you want to have the robot keep the teapot upright. That's the path constraint. And then the sub-goal, at the end of this stage, you want to have the robot to align the teapot spout to the cup opening. And then after it's aligned, it's only during this, while it's maintained to be aligned, you can start pouring by kind of designing this kind of pouring angle with the three key points. That's the blue at the handle, the red at the spout, and also the green one at the cup opening. And then all of these are used by constraint optimization solver to obtain the robot actions. And critically, if a path constraint gets validated, then it can backtrack to previous stage. For example, if you move the cup away, then it shouldn't keep pouring. You should kind of keep it upright again, realign to the cup, and then start pouring. So this enables the robot to kind of replan its action in closed loop at 10 hertz. And then here you can see kind of me just like being annoying to kind of try to mess up what the robot is trying to achieve. And then we also had a system that autonomously also complete all of these tasks, recycling can, placing shoes, where the robot has to figure out, okay, how it can place two shoes into this tight container, folding blanket that it needs to kind of align, collaborate with a human to fold the blanket together. And also stowing book where it needs to find out, okay, what's the sequence of action? I can place this book into this like really kind of constrained shelf. And then taping boxes, and also we did a long horizon case study of this task of preparing breakfast tray. So all of this does not require task-specific data or demonstrations. And all of the knowledge is coming from the foundation models. And also we did some cloth folding experiments where we literally asked the whole system, can you come up with strategies to fold this clothes without showing it how it can fold this different type of clothing, right? Yeah. Yeah, the tracking is done by a separate tracking module. So we in this way we literally use Dino V2, we compute its features per pixel, and then project it back to 3D, and then use cosine similarity to track them.
Do you find that reliable?
it's not reliable if it's occluded. So it needs to choose, you need to choose kind of where the camera is to be placed. The reason we use that actually is because we run the system on this 2 GPU machine, and then we need to run other modules. So it turns out that this is the most lightweight module we can run. If we have a more powerful one, I think some of the point tracker will be more reliable under occlusions. Yeah, but basically the idea here is whether the VLM and also all this foundation model, they can come up with the clove folding strategies like humans, right? Because we obviously will have different preferences, and maybe like each individual will have different preferences of how this clove should be folded. So here I've been talking about like the natural language, basically the evolution from the natural language task representation to 3D value maps, then to key point relations. So there's an evolution from text to 3D space and time. What about so later after this, we also did some extension works that investigate the task representation for each pixel at the pixel level, and also investigate the condition where if you have demonstrations, is there like a task representation we can leverage to allow the robot to generalize across tasks? So this is like really recent work. Actually, I literally just presented this earlier this week at Aa289. So here the idea is we want to represent tasks by affordance. So imagine walking into this room, you will immediately identify all sorts of action possibilities, right, afforded by the environment. For example, if you want to sit, the seat of the chair should exhibit high possibility. If you want to listen to music, the headphone ear cup should be highlighted. If you want to hold the bottles, the body should be highlighted. If you want to open them, then like the lid should be highlighted. If you want to instead, I think same goes for like watering plant and throwing trash. So the high level like method for this, we want to have like a model that can do this autonomously in the wild. So the idea is that we only collect, we want to design a pipeline that collect data autonomously. And the idea is that given any 3D object model, we first want to do multi-view rendering. And then for each render image, we compute Dino V2 features, which are fused into this like 3D feature field on the object point cloud. This is all in simulation. Then we perform class tuning to generate kind of the semantic regions for each for the object. And then we literally ask the VLM to brainstorm the potential tasks, as well as matching with the associated region. For example, it will say, oh, this cup can be used for drink, right? The task drink. And then the region that's relevant immediately for this like really, so we consider this like as a really fine-grained language. But that would be the kind of the blue region, which is the rim of the cup. I think the same goes for like if you want to grasp the cup, it will be this purple region. So the VLM is used to kind of give all of these annotations of which part matters for what tasks. And then we can compute feature similarity against the 3D feature field that we compute in the beginning to generate the continuous annotations. This allows us to train a model, the affordance model, to, like more than 10,000 object query pairs from behavior and object-verse. These are like the 3D object data set. And then using this, I don't have time to get into some details of the architecture, but essentially if you want to have this data to generalize to real-world scenes, you can build on top of the Dino V2 architecture, and this will enable us to have a model after it's trained, a single model to generalize in the wild that's task conditioned, and also, of course, in the wild, and also fine-grained, for example, identifying the color region for deformable objects, and so as where to grasp for the, if you want to open like an unseen drawer, and also hang close, right? Identifying where on the hanger you should pay attention to, and also where you should pay attention to for drink. But this is all can be run at actually at around 200 hertz on the modern GPU. And although this is like just a visual representation, but if you train an imitation learning policy with this representation, it not only can generalize to unseen poses, unseen instances of object, unseen categories, and also my favorite one is unseen task instructions, where somehow the video kind of froze a little bit. But if you ask a new instruction like watering plant, it can do similar motion, but for a different object. So we also recently released this and released like a online demo, and feel free to please check it out and then let us know your feedback. So that was representing tasks by affordance. But instead, if you also have demonstrations that's given in the beginning, so we can also use this as a task representation. So given some teleoperated interaction trajectories of the robot, for example, here you control the robot to kind of grasp a book and then store it onto the shelf. Then you can use foundation models to kind of really decompose this at both space and time dimension to basically construct a more fine-grained and composable kind of demonstration data. For example, for the same demonstration, it can be decomposed into grasping green book, adjusting the pink book, placing the green book on the shelf. And this is along the time dimension. On the space dimension, you can segment out the relevant objects. So the rest of the scene shouldn't really matter to, except for the relevant objects. So by training imitation learning policies on this data, and also have a long horizon planning framework, we can generalize to tasks that have different heights of the book and different geometric constraints, and even longer than the task horizon that's seen in the training data set. So that will be kind of close to the end of my talk, but I want to conclude it with with some closing notes that we have a high-level view of how this contributes to this task-level generalization. So recently, of course, there's huge efforts into scaling robotic data collections. While we have made great strides in many of the aspects of the problem, we still seem pretty far from having really the robot butlers in our home. So I really love, so what's missing, right? So I really love this plot from Andy. So the idea here is that we want to leverage internet scale data as something that's going from the top-down direction to approach kind of the robot intelligence that can provide the kind of the common sense. But here I want to offer a alternative or a more specific instantiation of the idea, specifically tailored for the task, kind of the task level generalization we care about. So due to the rapid development of existing foundation models, such as LLMs or VLM, we have seen emergence of a unified, all-powerful kind of symbolic intelligence. So this is kind of the intelligence that understands all of the nuances at the semantics level of what humans mean by a task and what humans need for a task. So intuitively, for those of you that are familiar with training RL agents in simulation and also the MDP formulation, this is more like a reward function that conveys the task to the robot. On the other hand, all humans have an intuitive understanding of how the world works, and they can improve their understanding from any type of interactions, regardless whether that's for a meaningful task or whether that interaction is a success or failure. In other words, we need to have a task-agnostic world model, and the world model should be spatial instead of textual. And by having this task-specific knowledge offered by existing foundation models to meet with this task-agnostic world model in a shared representation of this 3D physical world, I hope one day we can have robot butlers that operate autonomously in our homes that generalize across tasks and environments with purpose and generality. With that, I would thank all of my advisors and collaborators. Without them, all of this would not be possible. And thank you again for your attention and your time.
Yeah, I really like all of these works. I just one question that for a few of them, you use some sort of high-level LLM at the top, and then use the motion planning at the bottom. Do you think that's a good interface? Do you think motion planning is kind of useful and sufficient, or do you think that that's a big bottleneck?
Well, I actually think, so I would like to think all of this as something that's coming out of a model. Basically, I would think that there are two possible ways to get actions. One is by prediction, where you have a data set and you kind of use data set to kind of compile that into policy and then to predict action. And the other type of way is using planning or optimization, right? Where you have some model of the environment and you have an objective. And then this is a way that kind of you can have actions coming out of the void. But the void is not like just void. There has to be some models. So in many of this work, we use like simplified models. For example, for the key point one, it uses kind of the rigid attachment assumption, where the model is literally that if you grasp a key point, it will follow the robot anti-vector in a rigid way. But if we have a general purpose model, a world model of the environment, then we can kind of imagine kind of what the actions will be to accomplish some tasks. So I think it's more than, I guess you can characterize all of them as motion planning too, but over there it's driven really by a powerful world model. Yeah. I mean, it doesn't have to be planning too, because if you think of it as like an environment, then you can run, if RL can run fast enough, you're literally doing reinforcement learning within that model to kind of imagine and do a trial and error of what kind of actions would accomplish the task we care about. Yeah, planning is more like an online way that kind of start from scratch, which is not very efficient, but something that is easy to start with, yeah.
Thank you for your talk. It was really insightful. I have a specific question about the project you talked about where you use like DynaV2 to, I guess, segment out objects, and then you ask a VLM to like understand what those segments of the objects would be useful for.
Yeah.
Is there like a feedback loop in that process for determining how many segments of these objects you want to use, or do you kind of just leave that up to the model?
Yeah, that's a really good question. So what we observe is that we want to over-segment the object a little bit, because, but of course, I think your point is really valid. If there's a feedback loop, then the VLM can tell the other pipeline that, oh, I want more segments or something. I think that's a great idea. We haven't really tried it, but currently we just like over-segment more and then have VLM to choose, okay, which one matters for the task.
Did you ever find like examples of tasks that there wasn't a good segmentation of the object for?
Yeah. I think there is definitely some we found, and then some of them are coming from the segmentation pipeline, and some of them were coming from the VLM itself. But we did observe that on the VLM side, the error really decreases a lot, even in the course of the project. Like when they patch a new version of GT4.0, somehow it just gets better, and then I think other models also are pretty great too. Yeah. So we use the mean shift clustering algorithm. So over there, the idea is that you only set threshold in the feature space, and this is like empirically found, right? And then it would just try to segment based on that threshold by how many clusters you want. Yeah.
Okay. Yeah, let's do a little round call.